In this video, we're going to talk about conductivity of intrinsic semiconductor. We have seen the drift current in semiconductors, which is represented by J drift, and as it is a vector, we represent with a bar, which is given by sigma times E bar, where E is the electric field applied. Now, sigma is the conductivity of the semiconductor. So sigma is given by Q times N mu N plus P mu P, where Q is the electron charge, N is the electron concentration in the conduction band, and P is the hole concentration in the valence band. And mu N is the mobility of electrons, and mu P is the mobility of holes. In intrinsic semiconductor, N is equal to P, which is equal to Ni, where we called Ni as intrinsic carrier concentration. Now we can represent the sigma for intrinsic semiconductor. We'll say this is sigma suffix I, which is given by Q times, where N is Ni and P is also Ni. So we'll take this common out. So we have Ni times mu N plus mu P. We know that semiconductors are very sensitive to temperature. So let us see how the sigma, the conductivity of intrinsic semiconductor, is sensitive to temperature. Ni is represented as some constant A times T power 3 by 2 times e power minus Eg, the energy band gap, over 2 kT. We have derived this expression in previous videos, so I'm directly taking this expression from there. And mu N and mu P both depend on temperature to the power of minus 3 by 2. And same with mu P as well, which is depending on temperature with T power minus 3 by 2. Mu N, I'm taking proportionality constant to be some constant A, and we have T power minus 3 by 2 here. And similarly for mu P, I'm taking some constant, let's say B times T power minus 3 by 2. Now we know the expressions for Ni in terms of temperature and mu N and mu P in terms of temperature. So let me rewrite this expression, where sigma I is equal to Q times a constant A times T power 3 by 2 times e power minus Eg over 2 kT times the mu N plus mu P, which is A plus B times T power minus 3 by 2. Now T power 3 by 2, T power minus 3 by 2 gets cancelled. Now we have all constants, where sigma I, Q times A plus B times e power minus Eg over 2 kT. So all these constants, let me take it to be sigma I is equal to some constant, say C, times e power minus Eg over 2 kT. So if you observe this equation, it is exponentially related to temperature. So let me take this as starting point, where intrinsic semiconductor's conductivity is given by a constant C times e power minus Eg over 2 kT. And similarly, we can write the resistivity of intrinsic semiconductor, which is nothing but 1 over sigma I, which can be written here as 1 over C constant times e power Eg over 2 kT. Let us take ln on both sides, where I'm taking ln of sigma I is equal to ln of C plus ln of e power minus of Eg over 2 kT. Now we can represent this as ln of sigma I is equal to ln of C is a constant, so let me represent this as A prime, some constant, plus ln of this exponential can be written as minus Eg over 2k times 1 over t. Now let us try to plot this function with respect to 1 over t, where I am taking 1 over t on x-axis and ln of sigma I on y-axis. Now if we plot this function, we would get a line like this, where the slope of this function would be minus Eg over 2k. So if you see from this expression, A prime is a constant, and this looks like a straight line with slope of minus Eg over 2k. So that's what we're getting here. If you take an intrinsic semiconductor of dimensions, let's say this is length, this is width, and this is thickness, and let's say we apply a potential difference of, let's say V, and the current that flows, let's say, is I. Then we can find the resistance of this piece of intrinsic semiconductor, which is given by V over I. And we know this can be written as a resistivity of this intrinsic semiconductor times the length over the area. W times T. Based on this expression, you can find what is rho I, which is resistivity of intrinsic semiconductor, and we can find what is sigma I, which is 1 over rho I. So once we know sigma I, now do the same experiment at different temperatures and find out what is ln of this sigma I. Then we would get a plot like this, and if you see the slope of this, which would be equal to minus Eg over 2k, where 2k is a constant. So if you substitute, we would be able to get what is Eg, which means practically you can calculate what is the energy band gap of a semiconductor. So this is a practical way of actually finding out what is the energy band gap of a given intrinsic semiconductor. Now similarly, if you try to plot for the resistivity of intrinsic semiconductor, where I am taking x-axis to be 1 over t and y-axis to be ln of rho I, where we can write this ln of rho I is equal to ln of 1 over c, which would be a constant, plus Eg over 2k times 1 over t. Now if we try to plot this graph, it would look something like this, where the slope of this function would be equal to Eg over 2k. And again, instead of plotting the conductivity, ln of conductivity, we can plot ln of rho I, and we can find the slope of it, from which we can find the energy band gap of the semiconductor.